Page 170, section 3.5 is derivatives of trig functions. All right. To begin with, I need to remind you of a limit that we learned back in section 2.2, and then also prove to you another limit that we're going to pick up in this section on page 172. So to begin with, back in section 2.2, we talked about a trig limit. And that was the limit as theta approaches 0 of sine theta over theta is equal to 1. We're going to use that here in this lesson. Additionally, on page 172, they give me this limit law. Where does it come from? Well, if I use direct substitution, this is not well behaved. So let's see if we can use one of our algebraic tricks that we learned earlier this year for evaluating limits that are not well behaved. One of the things that we did was to multiply by the conjugate. Remember, that was the exact same numbers but the opposite sign in between. So I'm going to multiply by the conjugate of my numerator, and of course what I do to the top I also have to do to the bottom so that I'm not changing anything. So if I FOIL out my numerator, cosine times cosine is cosine squared. Cosine times positive 1 and negative 1 times cosine drop each other out, so negative 1 times positive 1 is negative 1. Cosine squared minus 1 is, according to our Pythagorean identity, remember the Pythagorean identity that sine squared plus cosine squared is equal to 1? If you subtracted the 1 over and you subtracted the sine squared over so that you rearranged that identity, you would have cosine squared minus 1 is equal to negative sine squared. And so that's what we've redone here, is we've replaced cosine squared minus 1 with negative sine squared using our Pythagorean identity. So I'm going to break that sine squared up to be sine times sine, and here's that negative out in front. I could replace the limit as theta approaches 0 of sine theta over theta with 1, because that was the rule from section 2.2. So I would have a negative times 1, that's where that negative 1 comes from. And then I'm left with just this limit. So let's try direct substitution. I'm going to put 0 in for theta, so that'd be sine 0 over cosine 0 plus 1. Sine at 0 is 0, cosine at 0 is 1, and so now this is well behaved. I'm going to get negative 1 times 0, which is 0. So we've proved this property that they gave us on page 172. We're going to use those two today as part of our lesson. So we want to look at the derivative of sine x, and we've talked before about how we can prove things informally and formally. I could go through and I could find the derivative of sine, or prove what its derivative is, by using the actual definition, and we're going to do that down here in just a moment, where we actually use the definition of derivative to prove something. But an informal way that I could prove this would be to use the tools we learned last week for graphing, where we could go through and we could say, okay, if f of x is equal to sine x, how could I graph its derivative? Well, the way that we did this was step number 1, we identified all the horizontal tangent lines on the original because they would be x-intercepts on the derivative. So that would give me an x-intercept at negative 3 pi over 2, negative pi over 2, positive pi over 2, and positive 3 pi over 2. Then we went back and we looked at where was the original function increasing, because its derivative would be positive there, and where is it decreasing because its derivative would be negative there. So increasing, positive, decreasing, negative, increasing, positive. So if this is switching from positive to negative at that x-intercept, then I can kind of sketch what's going on there. This is switching from negative to positive at that x-intercept, so sketch that. From positive to negative would look like this. From negative to positive would look like this. So to finish off that graph, I really just need some strategic points, right? Like I need to know maybe how high up this comes, and how low down this goes, and how high up this goes, and how low down, and how high up. And so I'm going to go through and plot some strategic points. So the way that we did that was we drew a tangent line at the point we were interested in. So I'm going to draw a tangent line at 2 pi. That to me looks to have a slope of about a positive 1. So that means that at negative 2 pi that my y value would be positive 1. And because we know that sine is periodic, that it repeats itself every 2 pi, I would get that same slope that I got at negative 2 pi. I would get it again at 0, and I would get it again at positive 2 pi. So just like I had the y value of positive 1 here, I would also have it here and here. Then I could go back and do something similar over here at negative pi. Hand draw a tangent line. Its slope looks to me to be about a negative 1. So that means that I could come down and I could say, okay, that's going to be a y value of negative 1 at negative pi. And again, the idea of a coterminal, whatever it's doing at negative pi, it would also do at pi. And so I could plot that value there as well, and I could keep going as long as I needed to. So if I go back and I play dot to dot with what I've got, what is that the graph of? Cosine curve, right. So I just proved informally by using a graph that the derivative of sine is cosine. All right, let's formally prove the derivative of cosine. So we're going to do the limit as h approaches 0 of f of x plus h minus f of x divided by h, of course our derivative definition there. So we could go through and let's put x plus h in the place of x, so that'd be cosine x plus h, minus the original function divided by h. Now this is cosine addition, so we reviewed that at the beginning of this year. Cosine addition is cosine, cosine minus sine, sine. That's my cosine addition formula. So now let's regroup a little bit here. I'm going to call this piece number 1, piece number 2, piece number 3. All that we're going to do down here is we're going to reorder this piece number 1, piece number 3, piece number 2. So all they did was just switch these two. So right here you can see they've just reversed their order. Didn't change anything, just reversed their order. Why did they do that? Because now I have a common factor of cosine x right here and right here that I could take out. So let's go through and let's take out that cosine x. If I take out cosine x, all I would have left here is cosine h. So that's what we did. We took out cosine x and all we have left is cosine h. And then if I take cosine x out of this, all I would have left is 1. So again, we've taken out the cosine x and all we have left is 1. Then here, I'm just going to break this into two separate pieces. So right now it's sine x times sine h in the numerator. We're just going to break it apart, sine x times sine h. And if we apply our limit, I'm going to break this apart and think of it as the limit of each piece individually. So right now I have the limit of that whole thing. Let's break it apart and think of it as the limit as 4 separate things. So if we start with that first piece, the limit as h approaches 0 of cosine x. If you put 0 in for h, there's no h in that, so it doesn't affect it at all. I'm just left with cosine x. All right, then if I take the limit as h approaches 0 of cosine h minus 1 over h, that's this rule right here that we just proved from page 172. That's going to be 0, so replace that whole thing with 0. Then this limit, if I put 0 in the place of h, there is no h, so that won't change. I'll just have sine x. And then this is sine h over h, which is the limit that we learned back in section 2.2 that we reviewed at the beginning today, that would be 1. So let's replace that whole thing with 1. So now we've got cosine x times 0, which is 0, minus sine x times 1, which is negative sine x. So we've just proven that the derivative of cosine is negative sine. All right? So now that I have proven the derivative of sine is cosine and the derivative of cosine is negative sine, I can use that to help me find tangent. Tangent is just sine over cosine. So if I'll rewrite tangent as sine over cosine, instead of having to use the definition of derivative, I could use some of my shortcuts. Like I could use quotient rule. I could say denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. All right, so the only thing new in that is that the derivative of the numerators would be the derivative of sine. We've just learned today that's cosine. And then over here, the derivative of the denominator, we've just learned today that the derivative of cosine is negative sine. So that's the only thing new that we've thrown in there. So we could say cosine times cosine is cosine squared, and negative sine times negative sine is positive sine squared. That numerator is my Pythagorean identity, sine squared plus cosine squared. That's 1. So we'll have 1 over cosine squared, and 1 over cosine is secant. So that would be secant squared. Right? So we've gone through and we've proven the first 3 identities. We've proven, or the first 3 derivatives. The derivative of sine is cosine. The derivative of cosine is negative sine. And the derivative of tangent is secant squared. So now if I were to prove the derivative of cotangent, I could rewrite that as cosine over sine and use my quotient rule. Or if I were doing the derivative of secant, I could write that as 1 over cosine and use my quotient rule. Or 1 over sine and use my quotient rule instead of having to go back to the definition of derivative. So now I have some tools to help me. You need to know these 6 derivatives inside and out, backwards and forwards for the rest of your calculus life. You will use them nonstop. So let me point out a couple things to you. If you memorize these first 3, it'll really help you with the second 3, because you'll notice that all the ones that start with C are negative. None of these started with C. They were all positive. You'll also notice that once you memorize these 3 formulas, these derivatives are just their reciprocals, like not reciprocals, I'm sorry, like if you think of the cofunctions, okay, like the cofunction of cosine is sine, the cofunction of secant is cosecant, the cofunction of secant is cosecant, the cofunction of tangent is cotangent. So if you learn the first 3, that gives you a jump start on knowing those second 3. However you have to learn them, you have got to know them. We're going to use them all the time, okay? So look at example 1. Example number 1 says if y is equal to x squared sine x, find the derivative. That's a product, so I'm going to have to use product rule, right? So I'm going to do first times derivative of second plus second times derivative of first, okay? So first times derivative of second, what's the derivative of sine? Cosine, right. Plus second times derivative of first, what's the derivative of x squared? 2x. Not really much simplification that we could do there. We can take that 2x and maybe move it out in front, but really that's all that we could do. All right, look at example 2. For example number 2, they give me a function and they say for what values of x does the graph have a horizontal tangent line, right? Remember, horizontal tangent line means that a horizontal line has a slope of 0, right? And slope of the tangent line is the same thing as derivative, so how did we find horizontal tangent lines? It is where the maximums and the minimums are, and yes, it is where the derivative equals 0. You're both right. So we need to go through and find our derivative and then set it equal to 0. All right? So let's look at this first piece. 2 cosine x. What's the derivative of cosine? Derivative of cosine is negative sine, right? So we'll have 2 times negative sine, or negative 2 sine. And then derivative of square root of 3x. Square root of 3. Remember when you take the derivative of x, it's just 1. So square root of 3 times 1, square root of 3. All right, so we said set it equal to 0, and we want to know where, for what x values do we have a horizontal tangent. So we need to solve for x. So what you going to do first? All right, let's subtract the square root of 3. Then what? Divide by negative 2. So I've got sine is equal to a positive square root of 3 over 2. So this takes us back to our trig review back in August, right? Been a little while. We need a reference angle. We need to know where our sine value is square root of 3 over 2. So that's going to be at pi over 3. That's our reference angle. Then where is sine positive? What 2 quadrants? First 2, right? So we need to give the first quadrant pi over 3, which is of course pi over 3, and the second quadrant pi over 3, which would be 2 pi over 3. Now, if they just asked me to give answers between 0 and 2 pi, then those would be my only 2 answers. If they say give all possible answers on the face of the earth, then remember all we have to do is take those 2 answers that we just found, pi over 3 and 2 pi over 3, and just tack on to them plus 2 pi n. And that goes back to the idea of coterminals. Remember that you can add or subtract 2 pi to find coterminals, right? So as long as n is an integer, a positive or negative whole number, 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5, 0, then basically all that would be saying is pi over 3 plus 2 pi times 1, or pi over 3 plus 2 pi times 2, or pi over 3 plus 2 pi times negative 1. That would just find all of the coterminals for that value. So again, by just tacking on plus 2 pi n where n is an integer, that covers every single possible answer on the face of the earth. Whereas if they just say find answers between 0 and 2 pi, we would only be given these 2 guys. All right, then they switch pace a little bit here and they go back to evaluating some limits. And the next example that we have is not actually in our textbook. It's a lead-in to example number 4 that I feel like we need a little extra work before we jump straight into example 4. So let's look at this one. For this one, it says, find the limit as x approaches 0 of sine 7x over 7x. And when I look at that, the first thing it reminds me of is that limit law that we had on the beginning of our notes today, back from section 2.2, that idea that the limit of sine theta over theta as theta approaches 0 is equal to 1. When I see the same thing in the numerator and the denominator, like a flashing light goes off, and I think there's got to be some way that it could be the equivalent of that rule. Well, that rule is when I have a single value, just like a plain x, not like a 7x. I've got a quantity here, so I'm going to need to substitute that out. So I'm going to say, let's let 7x be equal to theta. If I did that, then that would be the sine of theta over theta. So hey, now we're making progress. That's looking better. But if I replace this x with a theta, I also have to replace this x with a theta. So I'm going to have to come over here and say, okay, if x is approaching 0, then what is theta going to be approaching? Well, remember that theta is 7x. So I'm basically saying as x is approaching 0, what is 7x approaching? Well, if you put 0 in for x, that would be 7 times 0, so 7x would also be approaching 0. But I have to write that out for them. They have to see that. They have to see that I have substituted out not just the 7x in my fraction, but also the x in my limit notation. So now we can say, okay, 7x or theta is approaching 0, so now I have a perfect match for that formula, and I can say that limit would be equal to 1. All right, let's apply that then to example number 4. Because for example number 4, it says find the limit of sine 7x over 4x as x approaches 0. So I'm going to go through and I'm going to multiply the top and the bottom of that by 7. Why in the world am I doing that? Because I've got the 7x in the top, I need 7x in the bottom. By multiplying by that 7, then I can rewrite this, where I can go through and I can say, okay, I've got the limit as x approaches 0 of 7 times sine 7x over 4 times 7x. There's nothing magical in that denominator that says that I had to leave that as 7 times 4x. I can write it as 4 times 7x. I can multiply in any order. So you can see what we're creating right here is the sine 7x over 7x. That same problem we had just a second ago. And you've just got a constant 7/4 out in front, which, remember, the constant you pull out in front of the limit and get it out of your way and just evaluate the limit. So again, I'm going to need to state for them in this problem, okay, if I want to replace this 7x with a theta, if I replace this x with a theta, I also have to replace this x with a theta. So I have to write out for them, okay, since x was approaching 0, 7x would also be approaching 0. So then I can say the limit as 7x or theta approaches 0 of the sine of 7x or theta over 7x or theta. And then we just got our 7/4 out in front. So here's that same limit we did a second ago. The limit of sine theta over theta does give us 1. And we had our constant of 7/4 that we can multiply by our limit. Remember, you can do the limit first and then multiply by your constant second. And so that limit would be 7/4. Let's look at another limit that uses those two limit laws that we picked up today that involve trigonometry. Example number 5. Example number 5 says find the limit as x approaches 0 of x times cotangent x. Now, if I'm going to think of cotangent x, cotangent is cosine over sine. Most of us probably don't think of the cotangent of 0 off the top of our head. We would probably rewrite that as cosine over sine and then try and plug in the 0. And then we can see it's not well behaved. If I put 0 in here, the sign at 0 is 0. That's 0 in the denominator. So what I'm going to try to do is fix that denominator so that it becomes well behaved. And remember that we have that property that says if you have the limit as x approaches 0, which we do, of sine x over x, that's equal to 1, right? That was one of those two properties we learned today. So if I could get this to be sine x over x, then I could fix the problem in my denominator. So I want to multiply that denominator by 1 over x to create that limit law that we learned in 2.2. Of course, whatever I do to the denominator, I got to do that same thing to the numerator. So I'm going to multiply top and bottom by 1 over x. So in the numerator, I'm going to have x cosine x over x. The x's cancel out and just give me cosine. In the denominator, I'm going to have sine x over x, which is good. That's what I was trying to create. Remember that when you have the limit of a fraction, you're allowed to break that up into two separate limits, the limit of the numerator over the limit of the denominator. So in my numerator, I'm going to use direct substitution. I'll put 0 in for x so that I have cosine 0 or 1. And in my denominator, that's that limit law that we had at the beginning of the lesson today. That limit is 1. So now I can say 1 divided by 1, and my limit is 1. All right, so here is our homework for tonight on section 3.5. We're working on page 175.